Let's take a look at Cambridge A-Level H2 Math 2024 Paper 2. Let's start off with the section on the pure maths part first. We have here question number 1. It says that the complex number minus 2 plus I is denoted by Z. And for part A, we are supposed to find the real numbers A and B such that Z equal to A Z conjugate plus B. Let's write down the equation first. We have Z equal to minus 2 plus I. And for part A, we are given Z equal to AZ conjugate plus B. Alright, we can just replace our Z with minus 2 plus I. And we also know for Z conjugate is just simply minus 2 minus I plus B. And we can just do an arrangement of this one by grouping all the real part together and imaginary part together. We will be able to get like a minus 2 plus I equal to minus 2A plus B minus AI. And now we can do a comparison here, real part, imaginary part, and we can extract out two simultaneous equations. We will get minus 2A plus B equal to minus 2. Let's call this equation number 1. And for the imaginary part, we have minus A equal to 1. And we can call this equation 2. I think we have already solved A already. It's just simply A equal to minus 1. And from here, we can sub into our first equation. We can just say solving. We have A equal to minus 1 and B equal to minus 4. Alright, let's look at part B of this question now. And for part B, we are given a complex number 1 minus 3i, another complex number denoted by W. Without using our calculator, evaluate WZ minus W over Z, giving your answer in the form of C plus DI, where C are real numbers. Part B, we have WZ minus W over Z. Right, we are going to plug in the values of W and Z into this particular equation. Z is given to us as 1 minus 3i, and W, for Z will just be minus 2 plus I, and W is 1 minus 3i, Z is minus 2 plus I. And since this question we are not allowed to use our calculator, I think we got to rationalize this manually by multiplying the complex conjugate of the denominator, which is minus 2 minus I, minus 2 minus I. Alright, by doing our expansion, this case we will get a minus 2 plus I plus 6I minus 3I squared. As for this, I will end up with, for the denominator, will just be like a plus B, A minus B. I will end up with like a 2 squared plus 1, because this I times I give me minus 1 square, so therefore it's a plus 1. And for the numerator, we get minus 2 minus I plus 6I plus 3I squared. And let's further simplify this. I will end up with 1 plus 7I minus 5 plus 5I over 5, which will be 1 plus 7I minus 1 plus I equal to 2 plus 6i. Alright, even though this question did not allow us to use our calculator, of course, during our exam, we can just use our GC to do a quick check to see whether our algebraic manipulation is correct or not. Alright, let's take a look at question number 2. We have a gardener design a flower bed A, B, C, D, E in the shape of a rectangle and an equilateral triangle shown above here. We have the sides AE given to be A and sides ED to be B, and the total parameter is 20. Find the maximum possible area of the flower bed, showing that it is a maximum value. Alright, although it seems like this is a maximum minimum problem by doing differentiation, in fact, actually we can make use of our GC, because this question did not really say that we are supposed to use calculus or differentiation to solve this question. But anyway, I'm going to go for doing differentiation because I think the equation which we will be getting later on is pretty straightforward. It's quite easy to differentiate. Alright, let's do a quick sketch of this diagram first. we have this flower bed here, and this is A, this is B, this is A, E, B, D, C, and this is like a equilateral triangle, and we know that the length will just be A, and A. Okay, and since the first information they've given us is the total parameter of the flower bed is 20, perhaps I can come up with one of the equations first. We can see that we will have like A plus 2B plus 2A, A, 2B, and 2A here will just be equal to 20. Doing a bit of simplification, we get 3A plus 2B equal to 20, and hence we have B equal to 20 minus 3A over 2. I'm going to make use of this result to simplify the next equation I'll be having. And we are going to find the area of this flower bed here. And for area of this flower bed comprising of two parts, one will be the area of the rectangle, the other one will be the area of the triangle. Let me just write down area will just be equal to AB, length times breadth for the rectangle, plus I'm going to go for half AB sine C because this is an equilateral triangle. I will know that all this angle will just be 60 degrees. Using half AB sine C, I will get half AB, which is just A and A because both of the length of the equilateral triangle is the same. So I'm going to have a half A square sine 60 degrees. This can be simplified to become, and B, I'm going to make use of my previous part to become this. And for this part here, we know that sine 60 degrees is square root 3 over 2. Therefore, I will have square root 3 over 4A squared. Alright, if we want, actually, we can just key in this into our calculator and look at the graph and go and identify where is the maximum point. Alright, but as for saying that, I think I will just go for differentiation because I don't think it's very difficult to differentiate for this equation here. Maybe I can just let this be like a A, right? So therefore, I'm going to find my dA, d small a for this particular expression here. Just differentiate this, I'll get a 10 minus 3a plus square root 3 over 2a. Alright, and for turning point, I'm going to let my dA over d small a equal to 0, which is this expression here equal to 0. Square root 3 over 2a equal to 0. Alright, so from here, I will be able to get the value of small a that give me the turning point. Just expressing a in terms of the rest, I get 10 over 3 minus square root 3 over 2. Alright, and with this value, right, I'm going to substitute this value of a back into my expression for this part here. Alright, then just using our calculator, we should be able to get the area equal to 23.43 meters squared. Alright, but when we are doing differentiation, we have yet to show that this is actually a maximum. Whereas if you were to use your GC, you can actually just immediately tell whether is it a minimum or maximum. So this one have a slightly bit of disadvantage. But anyway, I'm going to show this one whether is it minimum or maximum by using the second derivative test. I'm going to differentiate this again. I'll get a d squared a over dA squared. Differentiate this, I will just get a minus 3 plus square root 3 over 2. And I can straight away tell that this is lesser than 0. Therefore, this is a maximum. And I can just imply that A equal to 23.43 meters squared is a maximum. Alright, now let's move on to question 3. And I think this question 3 is on a question on functions. We are given this function fx equal to minus x squared plus 4x plus 7. And part A of the question wants us to find the range of f. I think a better way of doing this question is actually just to plot this graph into our GC. And we can observe from the GC the sketch where is the range. Alright, I'm going to use my GC, which I did already, and when I use my GC to do a sketch, it will look something like this. And when I'm using the maximum function from a GC, I can in fact determine that the maximum point will happens to be given by x coordinate 2 and the y coordinates as 11. This is y equal to fx. Alright, and this actually is not presented in my solution. I just refer to my GC and just determine the range directly. And we can just say from GC, and the range will just simply be from all the way from negative infinity to 11. And I'm not supposed to include minus infinity all the way to 11. Alright, as for part B of the question, now the question wants us to sketch a graph of f, giving the exact coordinates of the point where the curve crosses the x-axis. Alright, and I think usually when the question says exact, most probably I cannot make use of my GC to determine the coordinates of it. Most likely the GC will return a decimal answer. Alright, we can try it, but anyway, I'm going to do a manual solving of the x-intercept first. I'm going to let fx be equal to 0, and the equation will just be minus x squared plus 4x plus 7 equal to 0. And I'm going to make use of my discriminant to discriminate the quadratic equation to find out what is the roots of this equation here. Okay, I'm going to use the minus b plus minus b squared minus 4ac over 2a. Alright, and let's do a bit of simplification. We get minus 4 plus minus square root 44 over minus 2. Therefore, we have 2 plus minus square root 11. Alright, in fact, actually, we can also find out what is the y-intercept very quickly. I can just say when x equal to 0, I will get fx equal to 7. Therefore, I know that the curve will intersect the y-axis at 7. Alright, I think that should be enough information for me to sketch out the graph. Therefore, based on what I have drawn in my part A for my GC, okay, now I can label some of the critical points. This point will be the maximum, which is 2, 11. This point here will be the x-intercept, 2 plus square root 11, 0. This point here will just be 2 minus square root 11, 0. And this point here will just be 0, 7. And I'm going to label this as y equal to fx. Alright. Okay, now let's move on to the next part of this question. Now we are given a function of g such that gx equal to 2 over x plus 1 with the domain from 1 to 10. We have to be careful. So when we are analyzing this graph of g, we cannot take into consideration all the values of x, only from 1 to 10. And for part C of the question, it asks, explain how you know that g inverse exists. And in order for a function to have an inverse, we got to satisfy one condition, and that is when the graph must be, the function must be a one-to-one function. And to test it right, we can actually use something called the horizontal line test. Let's do the question here. Alright, similarly, I think we got to do a quick sketch of this graph here. Gx equal to 2 over x plus 1 from 1 to 10. By using our GC, we can actually plot out the graph to look something like this, with the endpoints to be 10, 1.2 here, and this point here will just be 1, 3. This will be the graph of y equal to gx. Okay, and from the graph, right, we can actually see that no matter what is the value of horizontal line y equal to k that we draw, it will only cut the graph at only one point everywhere. So therefore, we can just write down from the graph. All right, the graph must be part of our solution here. A horizontal line y equal to k, where k belongs to the element of the range of G, cuts the graph at only one point. Therefore, G is a one-to-one function and implies that my G inverse will exist. All right. Now for part D, we are supposed to find the value of FG inverse 1.5. All right, let me just try to squeeze here for my part D. Right, part D, they want you to find G inverse 1.5. All right, usually for this type of question, right, if they give us some tangible value, like a value like 1.5 in this case, right, or some real constant value, right, I don't really need to determine what is the actual function of G inverse or F. All right, it's not really necessary, although you can, but it's a bit long. I'm going to kind of write down in this way. I'm going to let y be equal to Fg inverse 1.5 first. Okay, and right, for this part here, right, we can see that we can kind of let, I'm sorry, I'm going to let y be this part first. I'm sorry. All right, this part here first. Because this is the part that is giving me the trouble. So I'm going to let y be G inverse of this. Okay. Therefore, I can see that gy will just be 1.5. That means I kind of like uninverse the g. So I got a gy equal to 1.5. And we have the function of g given to us, which is this part here. So I'm going to replace my x with a y. So I get 2 over y plus 1 equal to 1.5. And from here, actually, we can already solve what is my y. And we know that actually y is actually this part here. Right? I'm going to now replace the entire g inverse 1.5 with my y equal to 4. All right, this part here is 4. Let me just indicate here. This part here actually is 4. So therefore, I can rewrite it as my Fg inverse 1.5 actually is the same as F4. All right, then therefore, this whole thing will just be equal to subbing 4 into my equation for my f, which is this equation here. So therefore, I get a minus 4 squared plus 4 times 4 plus 7. And this will work out to be a value of 7. Right? I think this is a much more efficient method than you are trying to find the new function of Fg inverse x. Right? That's the answer for my part D for question number 3. Alright, now let's discuss question number 4, which is on series and sequence question. We have the sum of the first n terms of the series of t given by this expression. And for part A, find an expression of Tn, the nth term of the series of t. Right, we have here, for A, we have Sn equal to 2n cubed minus 8n squared minus 4n. And actually, in order for us to find the general term, we can make use of this formula here, which is Sn minus 1. In fact, this formula can be applied to any kind of series, regardless whether it's AP or GP. Like in this question, we didn't really know what kind of expression is this, but yet we can still make use of this equation to find out what is my general term, which is my nth term of t. So we have Tn equal to Sn minus 1. Sn we have here, which is this expression 2n cubed minus 8n squared minus 4n. I'm going to subtract away Sn minus 1, whereby I'm going to replace all the n with n minus 1. 2n minus 1 cubed minus 8, n minus 1 squared minus 4n minus 1. And unfortunately, I think we got to expand out everything and to simplify it. And this is actually a cubic equation. We can either make use of our Pascal triangle or binomial expansion, or just simply make use of the rainbow method of expansion. I will get a 2n cubed minus 8n squared minus 4n. Alright, here we will have a 2n cubed minus 3n squared plus 3n minus 1. This we will have a n squared minus 2n plus 1. This is minus 4n plus 4. Okay, continue to simplify. We will have, let's remove the bracket at the same time. We will end up with a minus 2n cubed plus 6n squared minus 6n plus 2 plus 8n squared minus 6n plus 8 plus 4n minus 4. Therefore, the final result I will get is term n equal to 6n squared minus 22n plus 6. Alright, for the next part of the question, we are given another expression which is un equal to 50n minus 204. And part B wants us to find the value of n for which un equal to tn. I think I'm going to just do an equation of these two separate equations. Alright, un will just be like a 50n minus 204. This is just 6n squared minus 22n plus 6. Alright, re-expressing this, we'll get a 6n squared minus 72 plus 210 equal to 0. And we'll have a n squared minus 12n plus 35 equal to 0. You can solve this expression using our GC, or we can just do a quick factorization, n minus 5, n minus 7 equal to 0. Therefore, n equal to 5 or n equal to 7. Alright. As for the next part of the question, again, we are given another new series, which is Vn equal to 3n plus 60. Vn equal to 3n plus 16. Alright, and part C, find the smallest number greater than 100 that is in both series U and V. Series U and V. Series U is actually this expression here. Alright, and I want to find the smallest number greater than 100 that is both in U and V. Alright, I think the best way of doing this perhaps is to make use of our GC. Alright. For our GC, I'm going to key in the equation of 50n minus 204 as 50x minus 204. Since we know that x is an integer, I'm going to use the table to generate different values of n and the different values that it will get. Alright, and since the question wants us to find the value that exceeds 100, I think the first value that I will see is actually n equal to 7. Alright, but the thing is when n equal to 7, the value is 146. Right, I'm going to try. So when n equal to 7 is 146, I'll just plug 146 into this expression for Vn to check whether it is a valid value that Vn can take or not. Right, from here, I will try to solve this, and when I use my calculator to solve this, it ends up that n happens to be like a 43.333, which is not an integer, So therefore, I know that 146 definitely cannot lie in Vn. Alright, once this one fails, right, I'm going to go to the next value. The next value is 196. Right, same thing, I'm going to try. I sub in 196 into 3n plus 16. Alright, and this time around when you try to solve for the value of n, it actually gives me an integer, which is an integer. Alright, so this is a valid solution for both our un and vn. Therefore, I can conclude smallest number required basically will just be equal to 196. Right, that will be the answer for my part C. Alright, now let's look at part D of question number 4, we have here a series W given by Wn equal to 3n squared minus 5n plus 7. And part 1 of the question, explain why all the terms in this series are odd numbers. Alright, this is not a very standard kind of question. In order to show that it's always an odd number, we have to use some kind of deduction kind of method. And we got to consider different cases for different values for n. And I think the two big categories that we can segregate this question is to consider the first case where n can be even, and the second case will be when n is odd. Say for case 1, when n is even, alright, we are going to look at each of these value one by one. Like for example, let's talk about n squared. Right, when n is even, when we square a value that is even, right, like a 2 squared will be 4, like 6 squared will be 36, 10 squared will be 100. So therefore, we can come to a conclusion that n squared, it will always be even. Always be even. Alright, and if we were to multiply an even number by an odd number, it will still end up to be an even, because when you multiply a number by an odd, it will still be divisible by 2. It's always even. Alright, then it will just be even. This is for 3n squared. Alright, next we'll be looking at 5n again. Same argument here, if n is always even and multiplied by an odd number, it will still be even because it will still be divisible by 2. And next, we will have like 3n squared minus 5n, which is the combination of this case and this case. Alright, an even number subtract by an even number will again be an even number, because again this one can be divisible by 2 again. It will still be even number. Alright, you can just imagine that like 10 minus a 6 gives you a 4. So therefore it's still divisible by 2. Or 20 minus 8, you are left with 12, still divisible by 2. Right, because it's like when you subtract each other, right, it will end up still be even. It will always be divisible by 2. Right, now we are going to add in a plus 7 now. So we have a 3n squared minus 5n plus 7. And if you were to add an even number with an odd number, right, it will actually end up to be always odd number. Right, an even plus with odd will always definitely be odd. Like for example, 4 plus 3 will end up with 7. Alright, 10 plus 11, you end up 21. It will always be a odd. Right, that will be my case 1. So now we are going to consider case 2, whereby n is odd first. Alright, likewise, I'm going to consider step by step. I'm going to talk about n squared. And when we are squaring an odd number like a 3, when you square it, it will always end up to be a odd. Right, I can conclude that this one will be a odd. And if you were to multiply an odd number by 3, it will still end up to be a odd. And likewise, for 5n, it will end up always be a odd number. And 3n squared minus 5n, this time round will always be even. Because when we are looking at odd subtract by odd, right, it will always end up with even. Like for example, 11 minus 3, you will end up with 8. Alright, odd 21 minus 13, you will end up with 8 again. Alright, we can try to think of some examples of that, and we can generalize the result here. And finally, we can look at 3n squared minus 5n plus 7. Alright, in this case, right, it will always be a odd, right? When we have a even plus with a odd, right, it will always end up with a odd number here. Okay, right, therefore, I can come to my final conclusion. Wn will just be odd numbers. Right, now we have the next part of the question says that, can explain why series U and series W do not have any terms in common. Alright, I think I'm supposed to show that U will always be like a series that comprising of even numbers. All right. In order for this and my UN is given to be 5n minus 204, right? This is always already. And in order for them not to have any common members, this one definitely must be even. So I need to show that it will be even numbers. All right. So by looking at, sorry, I'm going to write properly. This is 50n. Okay. Right, we can actually see that, right, we can conclude that 50n will always be an even number. Right, because 50 is already even regardless whether you put n to be even or odd, right, this term here will always be divisible by 2. So therefore, it will be always even. And if you use 50n minus 204, again, is always even. All right, even minus a even will always give me a even. All right, so in this case, I can always conclude that, therefore, 50 minus 204 will not comprise of any odd numbers, since it is always even. All right, that is the part that I need to explain. Okay, that will be my answer for my D part 2. Now let's take a look at question number 5, the last question on the section A for pure maths. We have a graph y equal to fx intersect the x-axis given by a0 and also intersect the y-axis at 0, b. And the scale of x and y-axis are the same. All right, I think why they include this information is later on because we know that for inverse function is reflection about y equal to x. I got to draw my y equal to x like a 45 degrees. All right, if not, then you will be marked down because they already specifically say the scale of x and y axis are the same. All right, and basically the first part, I'm just going to do a reflection about the line y equal to x. 5a part 1. Okay, let me just draw the original one first. The original one will look like this. We have y equal to fx. This point here will be 0b. This point here will be 0a. Okay, I'm going to include y equal to x line here. All right, to show that for f inverse x, right, the graph actually is obtained by doing a reflection of my fx about this particular line here. Right, then it will look something like this, which is symmetrical about y equal to x line. This is y equal to f inverse x. And I got to do a labeling of this point and this point. For this, right, it will just be b0. The meaning means x for inverse is x become y, y become x. And this point will just be equal to 0a. Right, that will be the answer for my first part A, part 1. And for part 2 of the question says, again, we are given y equal to fx, and the scale of x and y axis are the same. Sketch the graph of y equal to 2f inverse x minus 1. Right, in this particular case, we have two transformations. One is applied to the x direction, the other one is applied to the y direction. This replacing x with x minus 1 means translation of 1 unit in the positive direction of x. And multiplied by 2 means it's like scaling in the y-axis by 2 units. Alright, I'm going to do a shifting to the right by 1 first. I can actually just make use of this particular graph which I've drawn in my part 1. And I will just do a shifting to the right by 1 units first. And I can kind of imagine when you shift to right by 1 units, All right, this point here, I can no longer label already because it's like somewhere around here already. All right, and the new y-intercept, I will not know. But this point here, actually, I will know because when I shift it to the right, the value of the x will just be added by 1. So become a b plus 1. Therefore, the graph will perhaps look something like this. This is y equal to x line. And it will probably look something like this. All right. It looks similar, but it's more to the right. And this point here will just be like b plus 1, 0. This point I can't label already. All right. And let me just label the original point A0. This point will just be a 0b. Okay. And this will just be y equal to 2f inverse x minus 1. It's like kind of wider because the value of the y are all multiplied by 2. All right, I think drawing this should be okay already. And now let's take a look at the next question here. All right, next question here, we have the graph of y equal to gx, intersect the x-axis at this point here, given here. And the graph of this, okay, g is gx, and we are supposed to sketch the graph of modulus gx. And we know that for modulus of gx basically means we are reflecting all the negative values of y upwards. Okay, therefore, it will look probably something like this, x, y. Okay, I'm going to keep this part here first. All right, this part here will still be the same because it's originally above the x-axis already. So therefore, it will look something like this here. Okay, and for this part, right, will be same. This part here is the same. This part here will be reflected up. Therefore, it will look like this, and this part here will be look like this. All right. We need to take note that this point here, right, actually is a sharp point. So do not try to beautify it to make it round, because at this particular point, the gradient actually is a finite value. It's not 0. So therefore, when you do a reflection up, right, this point here should be still sharp. Same way for this point, and also same for this particular point here. All must be sharp. All right, we are going to label whatever points that we can label. This was still the same. This is like 0v. This is u0. This is t0. And this is s0. Okay, finally, I'll just label my graph. Modulus of gx. Okay. All right, moving on for part 2. Again, we are supposed to draw the graph of the after the transformation g modulus x for this particular graph, which is our gx. And for g modulus x, right, is a bit different from what we have drawn just now. All right, the basic idea of this one means you are actually discarding all the negative values of x away. Then you will be doing a reflection about the y-axis for the part that is left over on the right side of the curve. After that, then you will end up with a symmetrical curve about the y-axis. Let me just draw it here. Okay, when we were to discard all the negative values of x away, right, we probably won't be able to label with these points where these 2 points are useless anymore. So we are just going to throw away this part here, reflect this right part to the left. Therefore, we will get a curve that looks like this. And again, right, at this interface here, it should be symmetrical. It's not very nicely drawn. Okay. This part here like this. Okay. At this interface here, this must be a sharp point. It cannot be round. Same thing as this point, this point, this point. This must be a sharp point. And this point will still be remaining as 0v. And this is the point is u0, the original point, the x-intercept u0. And when you do a reflection, actually this point will just be minus u0. I think that's about all. The rest of the things I wouldn't know how to label already. So therefore, this one will just be y equal to g mod x. Okay, that's about it. Okay, now let's take a look at part C of this question. All right, we are given the parametric equation x equal to 3t squared and y equal to 2t plus 3, and the values of t given to us is between -4 and 4. -4 and 4. All right, and we are supposed to sketch the graph. And for sketching our graph for this one, I'm going to make use of our GC. We are going to change the mode to a parametric mode. Then we will key in this equation. Then we will just sketch it. But be careful when we are sketching graph for parametric, we need to always change the window settings to change into the values of the parameter that we want. That means the range is from -4 to 4. All right. When we use our GC, we sketch the graph given by the GC, it will look like this. Okay, it should be round. Just draw nicer. Okay, and we are supposed to mark in the endpoints. The endpoints we can determine by using a GC, or we can just simply sub in the values immediately here, like endpoints here. I think using GC is safer because we can just try to press the value of t equal to 4, t equal to -4. It will actually give us the endpoints of it, which is 16, 11. This point will be 16 minus 5. Okay, and the thing is, right, if we want to find out what is this point here, right, I think we got to solve it manually. And for finding the x-intercept, right, basically I'm just setting my y to be 0 to find the t. After that, we will sub back here. So I'll just let y be 0, 2t plus 3 equal to 0. From here, I solve t equal to -3 over 2, which I can put back into here. Therefore, my x will just be equal to -3 over 2 squared, which will give me 9 over 4, which is the same value as 2.25. So with this, I can label as 2.25, 0 here. Right, and finally, we need to determine what is the so-called y-intercept. This point here, the curve is just touching. Again, I'm going to let x be 0. All right, I solve t equal to 0. Putting t equal to 0 back into here, y will just be 2 times 0 plus 3, which give me 3. Therefore, I know that this point will just be 0, 3. Okay, and finally, for part 3, right, we are supposed to, maybe I can just label this as curve C. Okay, and part 3 says state the equations of any lines of symmetry. Lines of symmetry means when you place that line across, the curve will be like symmetrical, like it acts like a mirror. I think I can immediately identify one line of symmetry, which is here. All right. Because when you were to draw a horizontal line y equal to 3 across here, this is a symmetrical curve. So therefore, the line y equal to 3 will be the line of symmetry. Okay, that will be the only line of symmetry that I can identify for this curve.